TE, or transverse electromagnetic polarization. Do y'all remember this class? I want to just, pardon me? I want to make sure everybody follows me on this. And again, this is oblique incidence, and this is one of the things that you have to at least appreciate, because we're going to get to something called Brewster's angle in a second. How many know that term, Brewster's angle? How many know what polarized sunglasses are? What do polarized sunglasses do for you? In a nutshell, in your own words.
They cut out like a certain
Glare, right?
Glare.
The word is glare. They do so by eliminating a component of light that's reflected that is really the TE component. And they pass the TM component that is the non-glare component. Now I'm going to get to this. This is important. But at least you appreciate the physics of that because you have polarized glasses, right? How can you tell polarized sunglasses from non-polarized? Anyone? If you have two pair.
They're normally blue.
Look at
the
the
screen.
the tinted.
You can rotate them and it blocks out light.
He's right. If you polarized sunglasses are basically very thin slits that will allow light with a certain electric field polarization to pass, but they stop anything where the polarization is perpendicular to the thin slits. Do you follow me? For the electric field. Now, if the thin slits are stacked this way, and you try to get an electric field through there in this direction, it won't work. But if you get it through this way, it'll permeate the slits, and this is the, I mean, it's a very, you might say, watered down explanation, but at least you can appreciate filtering requires something to differentiate different forms of things, right? And it's the same way, how would you filter, long pieces of wood that are oriented in this direction from that direction? You could have something that would allow the thin pieces in this direction to go through, but anything like this would be stopped. Now that's sort of trying to at least give you an appreciation for why we're doing what we're doing. So I'm going to recap the TE polarization. I gave you some problems. Frankly, it's plug and chug problems. There's nothing tricky about these. But for these, if I have region 1 and region 2, now in the real world, you would put in the axes you're going to use. They don't appear. So normally, you're engineers, you're intelligent. What you want to do is figure out, probably if we have two different regions with some eta 1, some beta 1, some eta 2, some beta 2, it would make logical sense to put the actual intersection of these two regions right at z equals 0, if you want to have z in this axis. Right? So this would be the origin. Do y'all follow me? It just makes sense. You with me? All this over here is a different material from the one over here. Now when you have TE light, or TE I should say, electromagnetic plane waves, you basically have an electric field incident, and I wrote out the equations for this last time, that's perpendicular to the board, right? And TE polarization means that at the interface, the electric field would be you might say it would be completely immersed in the plane that intersects the two regions. Does that make sense to everybody? I'm trying my best to find an easy way to explain this. But TE, if you want to think about the plane it's propagating in, the electric field is perpendicular. If you want to think of when it intersects, it has no component of an E field other than at the intersected surface. Do y'all follow me? There's no E field like this. Now the H field, on the other hand, it looks like that, right? And I'm just drawing this in a kind of a simple way. Y'all with me? It has to be perpendicular to the E field. It has to be perpendicular to the direction of propagation. That is the direction of propagation. Last time we talked about this, there would be an incident angle. I told you the angle that the field reflected would be the incident, right? Because of that phase constant stuff that we did when we got Snell's law. Y'all remember that class? All right, so I know this is true. I don't even bother with this. This angle is a little more important. This is the angle transmitted. Regardless if it's TE or if it's TM polarization, the way we always figure out what angle it's going to be transmitted in, or if we know the transmitted angle, what angle it came from, if it's a planar interface, we use Snell's law. And this works for any polarization there is. And it's basically beta 1 I'm gonna do one thing here. This is for lossless regions. I wanna tell you that when you get lossy regions, it gets a little more complicated and it's beyond what we need to cover in this class. It gets complicated, it's useful, but it's complicated. It's mainly for people that do geophysical work or people that are doing something where they're getting into exotic materials. So generally speaking, we talk about lossless material. It makes no sense to talk about high loss materials with these angles because the wave just gets shorted out. Y'all follow me? So try to appreciate the reasons for everything. So beta 1 times the sine of theta incidence is equal to beta 2 times the sine of theta transmitted. That is Snell's law. Let me shut my phone off. So that'll always give you the transmitted angle for the incident. We can check that box regardless of polarization. Now the thing you have to realize is the ratio of the transmitted electric field to the incident electric field is called the transmission coefficient. I usually put TE here. And that's equal to 2 eta 2 cosine of theta incident over eta 2 cosine of theta incident plus eta 1 cosine of theta transmitted. Now, something I'm going to say here, eta that I'm using is the intrinsic impedance of the region. All right, we're going to see in a second, we can also use something called the index of refraction. How many remember hearing the term index of refraction? All right, it has to do with light refracting or bending, right? I want to take just a moment and take Snell's law here and put it in terms of the index of refraction for everyone, because this is the most common way. All right, when we talk about an index of refraction, the symbol is N. Well, that looks a lot like my eta, doesn't it? Sure does, right? But N is the index of refraction. Technically, it's equal to the square root of mu relative epsilon relative. That's the technical definition for the index of refraction in the region. Now, we're assuming lossless. The truth is, almost everything we do is in a non-magnetic region. Y'all follow me in that class? Almost everything. Now, exotic materials or stuff, that's down the road. Have you heard of metamaterials in here? Anybody? You know what cloaking is? Do you know that term? It's something from, I think, Star Wars or Star Trek. It's when you literally have a wave. Suppose you had an object. Now, there's two things that can happen. You can send light at an object. If you have radar absorbing materials, nothing is reflected back. Y'all follow me? However, if you're looking from the other side, you'll see a zero there. You'll basically see something that's a dark shadow, right? And that's how come 2D radar, or should say bistatic radars, can see things with just RAM. Now, true cloaking is this. Just listen to me. And if you saw that movie Predator, they did a pretty good job showing. The electromagnetic field comes in, it hits the surface, and then it rides on the surface and comes out the other side, exactly as if it went right through it. Y'all follow me? The difference is the path it takes will cause a phase change. So with cloaking, there'll be a bit of a shimmer. Somebody will say, this is a logical question. Do they really have those technologies? The truth is yes and no. Yes, at one single frequency with the polarization of the electromagnetic energy coming in at one specific polarization, they can do it, all right? And they can't do it perfectly, but they can do it, and there is a shimmer, all right? The truth is, for any angle on an object to have that, it's well beyond anything we're going to see. Well, I say this, so many things have happened in my lifetime. It probably isn't going to happen when I'm around. Maybe when you're around, they're going to get to that point with all these, I hate to say this, machine learning is coming up with inventions daily that blow my mind. I don't know how they do that sometimes. But anyway, what I'm going to say is those type of things are called metamaterials, and they have what are called index of refractions here that can be imaginary or negative, and that's well beyond the scope of what we're going to cover. Do y'all follow me? This is material science stuff that gets pretty deep and pretty far out. Anyway, this is the index of refraction. So when we rewrite Snell's law with the index of refraction, I'm just gonna rewrite beta. We know that beta 1 is really omega times square root of u mu 1 epsilon 1, right? Times the sine of theta incident is equal to omega times square root of mu 2 epsilon 2 times the sine of theta transmitted. Now, I just rewrote this law with beta, of course, if it's lossless, being equal to omega times square root of mu epsilon. Everybody okay with that? All right, that's kind of second nature thing. Remember, just in case you've taken a break, gamma is alpha plus j beta is equal to the square root of j omega mu over sigma plus j omega epsilon, right? And if it's lossless sigma 0, then I get just beta over here for gamma. You all follow me, class? Just to make sure everybody understands what I'm saying. Now, what do you see here if it's lossless? Obviously, the first thing I can cancel on both sides is omega, right? There's a omega, or as a lot of people say, a w on both sides. That's supposed to be the Greek omega, right? Now I have this. If it's non-magnetic, hear me? Then the mu's cancel. Y'all with me? So I didn't put that here, but it's non-magnetic. So get rid of that. Now I have this. Well, index of refraction, if it's non-magnetic, is simply square root of epsilon relative. So really what this is the index of refraction for region 1 times the sine of theta incident is equal to the index of refraction for theta 2. And remember, this is index of refraction. I wish I could make that more scripty. Times the sine of theta transmitted. Agree? And that's Snell's law using the intrinsic, or using the index of refraction rather than beta. An index of refraction is much more common. How many have done physics problems with that, at least way back when you recall index of refraction? Everybody in here should have been immersed in that at some point. All right, whether you did it now or remember it, it doesn't matter. I want to make one comment about this. Now, this kind of makes it a little more applicable to your life. If this is air and this is water, it's called distilled water, fresh water, right? In fresh water, epsilon relative for, I don't know, 10 gigahertz up through about, I don't know how many gigahertz, even into the low optical range, epsilon relative is about 81. The reason we don't put 80 there is because we're going to do something in 1 second. Well, what does that make the index of refraction here? Square root of 81 is 9, isn't it, class? So that's 9. Now, that means this, in a nutshell, so you can see it applied. If this is water, everything down here is water, and this is air, if I shoot a beam of light this way, at an angle theta incident, it will bend, and it will bend towards the normal in such a way that, well, if I'm in air, the index of refraction for air is simply 1. So I can say the sine of theta incident is equal to eta 2 here. The index of refraction in region 2, which is 9 times the sine of theta transmitted. Do you all follow me on this? Now, you probably remember this. If there are bow hunters in here that ever shot carp or any kind of trash fish, you know that the arrow always bends downward when you stick it in the water. Anybody ever done this kind of stuff or know about bending of light through water, right? And so that means, let's just do an example. Suppose theta incident here is 45 degrees. All right? What's theta transmitted if it's water? Well, it would be what? Sine of 45 is 1 over square root of 2, right? So now I need to take the inverse sine, or a sine, of 1 over the square root of 2, right? Divided by 9 to find theta transmitted. Can you tell me what that is in degrees? You're going to see it's small. I don't know if it's under 12 or not, but it's small. And I have a point I'm going to make. in 1 second as soon as I get this. Right? This would be 1 over square root of 2, then I divide by 9, right? Take the inverse sine of that. What do you get? A sine is sine of the minus 1. Anyone?
4.5.
4.5 degrees, all right? 4.5 degrees is basically straight down. Y'all see this? Now, if I get at angles that are less than 45, this angle is going to go down even more, right? Now just think about this. So if I'm looking down, if I'm shining light, it goes in and bends almost straight down, right? Now hear me on this one. When light goes down and bends, and if there's an object here, it hits it, it's going to reflect back up that way. Y'all follow me? But the guy up here, if he's looking with his eye, what it looks like is the object is over here. Y'all follow me? How many see that right there? Now, the point is, if you don't know physics or you haven't had an experience, and I use this example because I've seen this actually. If you take a bow and then with an arrow and have it tethered to the actual bow, and you aim and you shoot at what looks like the fish, where are you going to shoot? Right over the top of them. Y'all follow me? So they always tell you in bow hunting and stuff, and this is true for a lot of stuff in general with physics. You shoot well below there. There's all sorts of rules of thumbs in this. And I mean, I'm just telling you right now, that's how severe the bend is just for water. That's not something where we're trying to make the thing bend to a vertical. Do y'all follow me? And that should make at least some alarm bells go off in your head. Hey, bending light around a thing might be possible if we could modify the index of refraction in a way so that you would get that. And the truth is, yes, you can, but not in this class now. I just wanted to show you. Anyway, that's Snell's law. And the reason I took this little, you might say, sidebar, is because I want to make sure when you get this kind of a thing for transmission coefficient, if you have the angle of incidence, you know how to get the angle of transmission. All the time they say, well, I don't know how to get that. You get it from Snell's law. Got it? All right. That's the transmission coefficient. The reflection coefficient, I'm going to put up there. A lot of this stuff, it's going to seem like it's just, you know, I'm all over the place, but it's all related to reflection from oblique incidence. So now, that's the ratio of the transmitted to the incident field, right? Now when I take a look at the ratio of the reflected field, this is the big one, by the way, to the incident field. It's given this symbol, TE. I'll do it this way. And that will always have the form of A to 2 minus some A to 1 over A to 2 plus A to 1. And here's where I go ahead and tell you how I get the coefficients. Now, you all see that that would be the reflection coefficient was normally incident. You all see that, class? If you're coming in when theta is 90 degrees, that's it. A to 2 minus A to 1 over A to 2 plus A to 1. You all remember that? And by the way, for a normally incident wave, it is both TE and TM. Right? The electric and the magnetic field that transverse the direction of propagation. Now, here, if it's TE, this is cosine of theta incident. You can look in your book, and this will be cosine of theta transmit. This will become cosine of theta incidence, and this will be cosine of theta transmitted. I don't know what page it's on, but you can check. Anybody got their books open to this so you don't have to take notes? I used to write my book all the time. I mean, I lose my notes. I won't lose my books if they're a couple $100. When I sat where you were, everything important. I can't say all the time, but if I could, I'd write it down in the book, like make notes that the professor suggested. You got, does everybody does anybody have their book open or not? Nobody, you don't have to, but it's in the book, is what I'm gonna say. People always worry about, oh, do I have to memorize this? No, I'll give you these formulas. You have to know what they mean. You all follow me? You have to know how to apply them and what they mean. All right, so now we have the transmission and the reflection coefficient. If I give you an incident field, you can tell me what the component of the field is transmitted, the magnitude, right? You can tell me the angle it's transmitted. You all follow me? You can tell me the reflected field and the angle it's reflected. You can tell me the magnetic field, and I didn't put it up here, but you all realize the magnetic field in any of these regions, because they're plane waves, is just a ratio of the electric field divided by eta in that region. Y'all with me on that, class? I don't bother with the magnetic field usually unless it's really important to do so, because I can get that fast. Okay, so that's TE polarization. Now TM is the one that has a Brewster angle. This one, I'll slow down a little, and you're going to see these will be modified slightly. And has anybody looked at OneNote in the last hour?
Not in the last hour.
You're going to see I put up some equations for you on purpose so that you will have access to these things without going to your book all the time. All right, now we're going to do TM polarization. That's the one where Brewster's angle becomes important. You can even say Brewster's. This will become important. So when we do TM polarization, if this is region 1 and this is region 2, here's the z-axis. I try to be consistent with Whitworth's book, X and then Y's out of the board like this. We're going to have a wave coming in at a certain angle, but this time the magnetic field will be perpendicular. Y'all follow me? In the electric field, now, in his book, I got to be careful when he draws this. This is on page 366, if you want to write it down. Here, if this is the magnetic field, H incident, the electric field is this way. Y'all follow me on this, class? Now, here's the important thing to see. Still the same angle of incidence. We can get the angle of reflection. And you might just say angle of reflection is angle of incidence, and we can get the angle of transmission from Snell's law. Y'all agree with this, class? We know this is this. It's a no-brainer, right? Reflection is incident. The transmitted angle we can get from Snell's law, correct, class? Just to be sure. Now, when you look at this, you'll notice the electric field is in the plane that it's propagating in. It's the magnetic field that's perpendicular, the magnetic field that's going to be parallel on the surface, the interface. Y'all follow me? Here's a very important point. When you take a look at the tangent magnetic field on this side, it would be the magnetic field reflected plus the magnetic field incident. Y'all see that? That would be equal to the magnetic field transmitted. However, and this is important, the incident electric field is not tangent. So the incident electric field's magnitude plus the reflected field magnitude at this interface is not equal to the transmitted tangent to the transmitted magnetic field, because they're not TE, or they're not all aligned. And please, I see this mistake, and I'll get to it in a second. They will see, well, I'll get the reflection coefficient as 0. Remember, reflection coefficient and transmission coefficient are ratios of electric field transmitted and electric field reflected, all right? Just please listen to me, all right? Now, you can have a 0 reflection coefficient for a TM wave. Now that has to do with the electric field reflected. Y'all follow me? But the transmitted field will not be equal to the incident because this angle, this bend, and I'll show it to you now in equations. Just appreciate what I'm saying. That's a common mistake. So when we do this, I'll just tell you how Whitworth does this, okay? He's gonna say H incident, and I know these equations bore you. That's gonna be some H naught incident, right? Well, tell you what, H naught incident, I told you this already, and this is the way Whitworth does it. He calls it E naught incident over eta 1. Do you all agree that's the magnitude? I told you if they're plane waves, that'll always be the case, right? It's going to be this. It'll be e to the minus j beta in region 1, and then comes that crazy x times the sine of theta incident plus z times cosine theta incident. I'm not going to keep rewriting that. I just want to put it in there one time to make sure you remember this, right? We did this. This is now sticking out, so it's in the AY direction. Y'all with me? I know a little bit, some of this stuff is a little uncomfortable to think about. Yeah, that's got to be the value of the incident H field. And everything revolves around the E fields when we do reflection and transmission. Just keep that in mind. That's the reason we didn't put H naught here and then work the E field in terms of H naught. So I have E naught incident over A to 1 times this. That would be out of the board, and that would be the correct mathematical statement of the incident field. Y'all follow me? Now, a unit vector in the direction of propagation for the incident wave would just be the cosine, well, I'll do it this way, sine of theta incident AX plus cosine of theta incident AZ. This is just as before. That's a unit vector in this direction. Y'all follow me, class? It's just like before, right? And always take a look at the extremes. Well, if theta incident is 0, then it's all AZ. In fact, that would be normal incident, right? Then take it to the other extreme when theta incident is 90 degrees, it's going this way. Sure enough, it would be all AX. It's a unit vector in the direction that the electromagnetic field is propagating. Got me on this, class? So I have that, and I know if I want the E field for a plane wave, the E field incident would be equal to minus A to 1. Do you all remember this one? Then it's times the unit vector in the direction of propagation, and it's crossed into the H field. How many remember me doing that? Some of these things will irritate you until you do several problems, and I'll give you sets of problems with this. Are y'all with me on this? This is just turning the crank in that. So when I do this, I have minus A to 1. That's the intrinsic impedance in region 1, times this, which is going to be the sine of theta incident AX plus cosine of theta incident AZ. And then it's crossed into the H field. That's the H field. You're going to see something that some of you probably realize now. I just wrote this down one time. Okay? We have the H field, now we're getting the E field. You all follow me? One thing you see looking at this, before I just run the math on this, just watch. You see you have A to 1 there, it's over A to 1. You would expect E to be a value of E naught, and without any of that crap. Yeah, that goes away, thankfully. Now, next, I'm not trying to go fast here. If you need more time, I see people writing. I'm trying to make sure everybody sees what I'm doing. Just appreciate this. We're going to get to the final form of what you need to know in a second, but appreciate what's going on. Now, when I do the crossing, I have AX crossed into AY is AZ. So what I'm going to do is just make this AZ. And then when I have AZ crossed into AY, I get minus, right? It's minus AX. So I just put the minus AX here. And get rid of that. And that, in fact, is the form that's in Dr. Wentworth's book. Y'all with me? Now, because there's a minus sign here, what happens, this becomes minus, and this becomes plus. And if you look in your book, if you have it, you're going to see that's the form of the incident electric field. Now, here's another thing that helps you see this. You see the magnetic field's coming out, right? You all see how I drew E? It's perpendicular to the direction of propagation. And if you take your right hand and put your index finger in the direction of the E field, and then rotate it into the H field, you see your thumbs pointing in this direction. Can you all see that, class? How many can? Right? All right. E is what? Crossed H is that way, This thumb points in the direction the wave's propagating. Y'all see this? Now here's the thing, you see how the E field has a negative Z component? Just take a look at the projection. Negative Z but positive X. Do y'all see that, class? Did we do that right? Yeah. Negative Z, positive X, check that box, it works. That's how you get the electric field in all the regions. By the way, for the transmitted field, I'm not going to do this right now. The only thing that changes for the transmitted field from this equation is this becomes transmitted, all right? And then also beta 1 would become beta 2. This is transmitted right there. And then E naught incident becomes E naught transmitted. Do y'all follow me? Same exact form. However, when we get this guy over here, the reflected field right here, and in Wimmer's book, he's going to have the H field, I believe, going into the board on this one. I'm not a fan of this. I like keeping the, if you're talking about using the H field as the primer to get everything, keep the direction consistent. For this one, he has it going into the board. Here, I have the H field sticking out of the board. Here, the H field would be sticking out of the board. But now here, this is just Wentworth. He has the H field going in. So he's going to say, I'm going to have the H field going in. The reason he does this is this. If it's going in, now I can put my E field this way. And I know E cross H is direction of propagation. That's the reason he did it. And some of you are going to say, well, Dr. Baginski, won't that change everything in terms of reflection? No, because the reflection and transmission coefficients have to do with the E field. Hear me on that? Remember this. Now, I could put, and in your book, there are the transmitted and the reflected field equations for this, okay? Once we'd write them, it gets a little boring to you. I'm going to let X and Y go to 0. Get rid of that exponential, just hear me. Just the way I did before. I'm going to, in doing that, I would be at the boundary, at the origin. The only thing I do is set the tangent value of the E field on one side equal to the tangent value of the E field on the other side. Remember what we did before? And I would set the tangent value of the H field equal to the tangent value of the H field on one side equal to the tangent value on the other. Y'all hear me? Just like we did for TE polarization. The result, which you want, I would work this if you want me to, but this class looks like they're just hanging on by fingernails, right? I mean, between the masking and everything else, I think this would be a little over the top. If you want, anybody want me to do it right now? It's like, I don't know what you're talking about. All right, here's what happens. The ratio of the reflected to the transmitted field, or the incident field. So this is the reflection coefficient for TM. This is important, TM reflection coefficient. Just listen now. It will have this, I always do it this way when I'm trying to teach people. It's going to have A to 2, and it'll have A to 1. There'll be a minus sign, A to 2 plus A to 1 like that. Just like, I've always put those up there, A to 2 minus A to 1 over A to 2 plus A to 1. Now the coefficients of those change from the actual TE. Here, before, it used to be what? It was the cosine of the incident wave, right? Now it's cosine of transmit. Take a look in your book. And this becomes cosine of theta transmitted. This becomes cosine of theta transmitted. This, this is incident part. This becomes cosine of theta incident. And in his book, he has this, actually, he puts the coefficient, he doesn't do the ratio like I like. What he does is put E naught reflected. This is on page 367. And, yeah. Follow me? Again, that is the transmit, or I call it the second angle. Now, the transmission coefficient for TM is equal to E naught transmitted over E naught incident. And it's not equal to 1 plus. This is real important. People always say, well, it's 1 plus reflection. Not for TM. All right, got me? Because it's the E field. The E field does not have that because the E fields are not parallel to one another. E fields, you know, TE polarization, they're parallel at the interface, they're not here. So this is equal to 2 a to 2 cosine of theta incident over a to 2 cosine, and here you're going to see theta transmitted plus a to 1 cosine of theta incident. And I think this is the way Wentworth has it. There's a couple different forms. Yeah, if this is a formula 6.142, if you want to look in your book.
4.2 or 4.3?
6.142, you see? Now, 143 is an abbreviated form. We use 1 plus the reflection coefficient that has a ratio of cosines. Right, you see it there?
This one?
I use this one. Now, here's the reason I'm saying it's important to follow this. When I look at this right here, this is never going to be 0 unless that angle cosine of theta incidence right there becomes 0, which means theta incidence is 90 degrees. Y'all see that? Everybody with me on that? However, we can get 0 effective reflected electric field, now just listen, if we make this 0. And in fact, we can solve for that. It's called Brewster's angle. So I want you to listen to me. When the reflected field is 0, that's Brewster's angle, right, for the TM mode. So here, now I'm going to do it over here. And this will be, everything will be transmitted. Nothing will be reflected. But the thing is, when it's transmitted, this isn't 1, because the electric fields are not in the same, they're not perpendicular to the interface. In other words, a cockeye. Right, the magnetic fields on one side equal the magnetic fields on the other side. And the transmitting magnetic field is the same as the incident at Brewster's angle. But here's what happens. When we talk about Brewster's angle,
Dr. Gibb,
yeah,
can you repeat that again? When the reflection angle is what? Brewster's angle?
what happens is Brewster's angles will be when this goes to 0. Nothing when nothing reflected, everything transmitted. You all follow me, class? Sorry, I might have said that wrong. Everything is transmitted, nothing reflected. It only works for the TM case. So for the TM case, we have the reflection coefficient for the TM case equal to 0, equal to a to 2 cosine of theta, and the way I've done it, I have theta transmitted minus a to 1 cosine of theta incidence equal to 0. Do y'all follow me? I'm just setting that reflection coefficient equal to 0. That is the definition right here of Brewster's angle. It's for incident light. It would be the angle light comes in for the TM polarization where nothing is reflected. Y'all follow me, class? Everything is transmitted. Okay, so how do we go about solving this for this magical angle, right? Here's the thing, this equation, we'd assume we'd know the material parameters, a to 1 and a to 2. But if we look at this, we have 2 unknowns, right? So how do we get it? We use Snell's law. In Snell's law, it says what? Beta 1, I use beta 1 times what? Sine theta incidence equals beta 2 times cosine of theta sine of theta transmitted, sine of theta transmitted, right? Correct? That's Snell's law. Now I know beta is really omega times square root of, so here we're going to do something. We're going to do this, we're going to assume mu relative equals 1, so it's non-magnetic. And therefore this becomes square root of epsilon relative 1 here times sine of theta incident equals square root of epsilon relative 2 here times the sine of theta transmitted. I'm just trying to show you, now you have 2 equations, 2 unknowns, you can solve for either one, right? We want to solve for the incident angle, and now we're going to call that incident angle the Brewster angle. So what Dr. Wentworth does, he simply calls this the Brewster's angle. The Brewster angle. And now, I can do this line easier than you can. I'll just make this BA, right? Nothing fancy here. Now I go ahead, and what I really want to do is replace this cosine with this value, or vice versa. It doesn't matter how I do this, but let me do it this way. If I look at this right here, this equation, I'll take this. You don't have to do this. That's eta 2 cosine of theta transmitted equal to eta 1 times cosine of theta incident. Do y'all agree with that? Right? Now what I'm going to do is take a ratio of these two things, because I want theta. I'll divide both sides by first theta, or by eta 2. Now that's still eta. It's not the index of a fraction. I'll call this dA, Brewster's angle. Right? Then after that, now remember, eta is equal to square root of mu over epsilon. It's non-magnetic, right? Take a look at this. This would be the eta 1 over eta 2 would be square root mu 1 over epsilon 1 over square root mu 2 over epsilon 2, right? Since it's non-magnetic, the mu's cancel, right? What else happens? Then I get this equals to the square root of epsilon relative 2 over epsilon relative 1. Correct, class? Y'all see this? Maybe you can you see it or not? You don't have to write this down, just appreciate this, please. So if I take this and I stick it in there, now I've got cosine of theta transmitted is equal to square root of epsilon relative 2 over epsilon relative 1 cosine of theta Brewster angle. And now I go ahead and square both sides. Y'all follow me? When I square both sides, I'll do it here. Now I get cosine squared of theta t, which is equal to 1 minus sine squared of the transmitted angle, is equal to simply epsilon relative 2 over epsilon relative 1 times cosine squared of the Brewster angle. Cosine squared is 1 minus sine squared. That's the only reason I did that. Okay? This is the old trick, and Wentworth uses this in his book. There are other ways to get it. Now, at this point, remember, I just want theta t here. I want sine of theta t, so I can stick it right there and just have one equation with the Brewster. Follow me, class? Without a lot of rigmarole. If I take a look at this, forget that for a second. And what I'll do is multiply through by a -1 first, just so everybody sees what I'm doing. And then I'll add 1 to both sides. Agreed? Y'all follow me on this? And then what I'll do is this. I'll simply take that sign right there and replace it with, I'll square both sides first. So I have epsilon relative 1 times sine squared of theta Brewster angle equal to epsilon relative 2 times this mess, which is going to be 1 minus epsilon relative 2 over epsilon relative 1 cosine squared of theta Brewster angle. Y'all see this, class? Now you can see what I'm up to, right? I've got it down to that point. Now I can manipulate. Oh boy, trying to do this without. Let's see here. I'm ultimately going to take that cosine, take it to this side, and I could get a tan form, but I'm going to have a leftover part. Anyway, in his book, when you get this thing, you're going to get the sine, he'll have the sine of theta BA, but I can do it this way. Just make this 1 minus sine squared here. And then what you would do is collect the sine terms together. I'm just going to get to the bottom line because we're about out of time. And you'll find out that the sine of the Brewster angle will be equal to, it'll be the square root of 1 over 1. And the way he writes this thing, he has in 6.146 the entire formula, but he does have just a, he doesn't have it in terms of it's epsilon relative 1 over epsilon relative 2. For this one, let me just see something here. That would be plus, comes to this side. You're going to get something that gets a little messy, but this is ultimately the Brewster's angle. Keep in mind, you don't have to solve it like this. There are several other ways. There's tangent formulas I can give you and different other ones. I'm trying to just show you his approach. But the key thing is this reflection coefficient goes to 0 for Brewster's. Now, gotta say this, when this goes to 0, this doesn't. This doesn't go to 1. For a TE mode, if the reflection coefficient goes to 0, the transmission goes to 1, but not for TM, and that's real important, okay? Just remember that. All right, that's it for oblique incidents. And some people are going to wonder, well, what kind of problems would we'd be responsible for on Friday? On Friday, if I give you an oblique incident, I would ask you for the angle transmitted, if I gave you the angle incident, or vice versa. And if I showed you a wave, I would give you the reflection and transmission coefficients for TE and TM. I would expect you to be able to get the transmitted or reflected electric field values. Do you follow me, class? Now, these are strict magnitudes. I don't expect you to do anything really crazy and prove anything. This is not a math course, so I'm not going to ask you to prove anything. Now, in physics, has anybody had advanced physics here? If you take mathematics or physics, especially at the 400 level or higher, with the graduates, they will ask you to prove things. I don't do that. This is engineering. It's all applied. All right? Just appreciate the reason for it. I didn't even have time to prove it today. We're not